So the official name of this shape, donut shape, is Taurus. Okay, let's get the dimensions. When we say capital R, that's the distance, the radius going inside the donut from the center to this part. And lowercase r is the radius of that little circle, the cross section. So the way you achieve that is if you have, this is the origin, circle with the radius lowercase r, and revolve that thing about this, x is equal to negative r, so distance from here to here is negative r. You know what I'm saying? And then that will create this donut. Now, at this point, I want you to make a prediction. Which method would be easier? We're going to do both, but at least make a prediction. Washer or shell? Which do you think would be easier? Feel free to speak out.
Washer?
Washer? Well, I have a vote for washer. Does anybody vote for shell?
I'll vote for shell.
Okay, so we have a split vote. Should we put it to, well, like, have a democracy that the majority decide? Something about truth is not really about democracy now, is it? Right? Truth does not care how you feel about it. So we have a mixed feelings about this. We'll do it both ways and we'll find out. Okay? Okay, so let's go. I'm going to draw the rectangle. We'll do washer first. So let's draw that rectangle about here, like so. See, in washer technique, this rectangle is perpendicular to the rotational radius, right? So if I rotate that thing around, then it creates this shape, which is what we call washer, industrial washer. It creates this looking shape. Change the color, and I'm gonna draw that looks about right. And then you have to be pretty artistic in this business. So I messed up already. When you're doing art sketch, use tiny little line segment instead of just one stroke. I still messed up. So why am I bad at art? Actually, I was pretty bad at art. I never got art. So it creates something like this, right? And that inner radius probably is somewhere there. You know what I'm saying? Oh, not bad. Okay, let's get the dimensions, okay? So if I call these functions, this is x1, I mean x2, let's say, and this is x1, whatever those are. And let's just figure out this outer radius first. This is what I used to call capital R, but I don't want to call it R anymore. And reason for that is because I'm using capital R here. You know what I'm saying? So we'll just say that's a big radius. And what is that big radius? When we say x, x is from here to here, correct? So this is x2. And then how much is then this much? This much is R. Do you get it? So do you see this is R plus X, or X2 in this case? Say yes. Okay, so far so good. Okay, now what about the small radius? Oh, I regret drawing it there. I'm gonna draw R down here. Okay, then what about the small radius, which is this? Right, and you might think, oh, that is of course R minus X1 then, isn't it? Or is it? What do you say? Am I right or not? Have no idea? Okay, let's write down what this x1 and x2 are. So equation of this circle, of course, is x squared plus y squared is equal to lowercase r squared, correct? So this one on a positive side is square root of r squared minus x squared a. What is x1 then? Negative square root of r squared minus y squared a. Did I write x here again? Y squared. You see, this is negative number, isn't it? Because it's on the left-hand side. This is x1. Which means we cannot write negative here, because if I write negative and substitute that thing, this will be plus again. You know what I'm saying? So I have to write plus here. Good? Does that make sense to you? Okay, I'm going to write dv. It'll make more sense once I simplify it. dv here is, so we have pi, and then this thingy, r plus x2 big radius minus r plus x1 squared, and then dy, and that thickness is dy for the time being. But let's simplify this. So r, and then x2 is square root r squared minus y squared, and minus, and then we have r, and then plus negative square root of r squared minus y squared, quantity squared, dy. Does that make sense to now? Because one, here, this one you add and this one you subtract to create the outer radius and inner radius. Very good? Yes? No? Maybe? Who's confused? Let me know right now. Okay then. Unthinkable. We have to multiply this out and then like terms, and that is just too much algebra, isn't it? So we're going to do it in our head. It's a lot easier than it looks. Watch. This becomes r squared, right? And there's an r squared and we subtract, so r squares cancel. But look at this thingy. If we square this thingy, r squared minus y squared minus r squared minus y squared, so those two cancel. Only thing that survives is the cross term, isn't it? 2 times r times square root minus negative 2 times r times square root. So we have 4 times r times square root, 8. With that pi, we have 4 pi r square root r squared minus y squared dy. How about that? Too much algebra? Nah, yes, no, maybe. Okay, moving on then, let's integrate. So our v is equal to, from now we could use symmetry from here to here and instead of negative r, right? However, see, I figured out from second period, in order to enhance the understanding for the shell method, actually I'm not going to do that, and I'm going to just come out here and negative r to positive r. I just do this, okay? There's a reason, trust me on this. And then I'm going to write down 4 pi r and square root of r squared minus y squared and dy. Okay, so I'm going to cover all of this from here all the way there. Good? Okay, now what is the technique of our integration? How do we integrate such a thing? Somebody make a suggestion? Oh, come on, feel free to jump in anytime.
4 pi r, since you can move it out.
Yeah, this moves out, and then what do you do about this square root thingy? Somebody, I think, was about to say it.
Trig substitution.
Trig sub. Okay, good suggestion. With what? Which trig function do we use? when it's in this form?
Is it sine?
Yes, it is sine. And are we missing something in front of sine?
R?
R, of course, right? And those of you who never understood trig sub, here's a quick recap. The motivation is this, right? I want to simplify this. And let's see. So here's r squared. And if I substitute that e, I get r squared sine squared theta, correct? Now let's simplify that common factor r squared, and then we have 1 minus sine squared theta. This is why we put r here. Then this thing is cosine squared theta now, isn't it? So we have r cosine theta. You get it? Do you finally get trig sub? Okay, then having said that, we also need dy. So dy, I'm going to calculate here. dy is equal to derivative of that, which is r cosine theta and d theta. Okay? Substitute both of them in. So what we have is this now. So we'll take 4 pi r outside, and then integral of this thingy, which is r cosine theta, with another. So we have r squared cosine squared theta. Oops, just one notice acting up. D theta. How about that? You with me? Okay, now the second thing we need to do is we have to change the limits of integration because we changed the variable to theta. So from y, so when y is equal to negative r, let's substitute negative r here. That tells you sine theta is negative 1. That means this lowercase is negative pi over 2a in order to get negative 1. And if we substitute r here, that tells you sine theta is positive 1. So theta should be pi over 2. Still with me? Okay, then cosine squared theta. How do we integrate cosine squared theta? Identity time again. Why don't I review that as well? See, it starts with cosine 2 theta. And originally this was cosine squared theta minus sine squared theta. At least remember that much after identity quiz. But one we need is this cosine squared one, isn't it? So cosine 2 theta is equal to substituting 1 minus cosine squared for the sine. So we have 2 cosine squared theta minus 1a. Which means now finally this cosine squared theta is equal to, like that, so 1 plus this way, so 1 plus cosine 2 theta over 2. Y'all get it? This will be on many different tests. So substitute that thing here, okay? Which means this 4 and 2 will cancel. So we have 2 pi r, take the lowercase r squared out, and then we are going to have 1 plus cosine, that looks ugly, cosine 2 theta and d theta. You with me? Questions? Okay, usually this thing doesn't contribute much, and you'll see why. This is why, usually, not always. So we have 2 pi r lowercase r squared integrate, so we have theta plus, that thingy of course is sine 2 theta. Let's check by differentiating. If I differentiate this, I get cosine, so plus sine is correct. Chain rule, 2 comes out, right? Which means I need 1/2 here in order to offset that 2. And from negative pi over 2 to pi over 2. Still with me? Okay, now if I substitute negative pi over 2, I get negative pi over 2. This thingy becomes sine pi, that's 0. That's why this thing usually doesn't contribute much. Minus negative pi over 2. So between the two, I pick up pi, right? And this thing, once again, gives you 0. So I just pick up pi from this whole thing. So what I have is 2 pi squared r small r squared is the volume of that donut. How about that? Questions? Okay, now we shall. Okay, I have that thingy, copy it down here. I'm gonna move it up. Okay, now for shell, we have to draw the rectangle parallel to that rotational axis, and then we revolve this thing. Wait. Oh, okay, I'll just do that first. About this way, right? Like that. Change the color. I'm gonna change the color of this one to red, like I usually do. And then throw the outer thingy like that. I made that thingy too thin, but hey, wait, I don't like it. A little prettier now, right? Okay, and it'll come down about here, right? Okay. So we create something that looks like this, which is an infinitely thin paper type of cylinder. You with me? Okay, so this is my dV. Okay, let's write down the dimensions here. See, this much is y, so we have 2y from here to here. And that thickness is dx, isn't it? So only thing we need to figure out is this rotational radius, okay? Just like before, isn't it? R plus x. Good. Do you see that? If I write it down again, this much is r. This much is r, isn't it? And that is x. Whoa, did not want to do that. How about that? Okay, so let's write down the expression for dV. My dV here is 2 pi times the radius, right? The circumference, so 2 pi, in this case, r plus x times the height, which is 2I, and the thickness dx. Good? Say yes. Okay, that happens to be now 4 pi r plus x, and what is my y here then? Y here is of course square root of r squared minus x squared, eh? Equation of a semicircle, upper half. So square root of r squared minus x squared and dx. So far, so good. Okay, we are ready. Do you see the trouble bubbling up in the horizon? How many of you see it? My V. Now, we cannot use symmetry in this case. Why don't we go from 0 to r and double it? No, this outer side travels farther around compared to this inner one. So the outer one is so much more volume. You know what I'm saying? See, when I was young, we grew up in a poor family in third world country. See, South Korea in 70s used to be a third world country. And then when we have to share little things, snack, in order to make it fair, we always had this policy. I'm gonna cut and tell my younger brother, you get to choose which piece you want. That way, that will ensure that I will cut it fairly. You know what I'm saying? But suppose I did that, instead of slicing the bagel sideways, so it's like, if this is the side view of the bagel, and instead of sliding it this way, let's say this is the top view of the bagel. And then if I carve it like that and say, this is the same, you take the inner piece, and my brother is not that dumb. He will probably say, I want the outer piece. You know what I'm saying? Because this is bigger, isn't it? Don't you see this is a lot bigger? Yeah, it's like that. So symmetry doesn't apply in this case. So what we have to do is, I'm going to change the color to blue. So we have to go from negative r to positive r, okay? And then put this whole thing in. So 4 pi, and then r plus x, and then square root of r squared minus x squared dx. How are we going to integrate this? Unfortunately, we have to distribute this and separate it into two separate integrals. So what we have is 4 pi r constant from negative r to positive r of square root of r squared minus x squared dx plus 4 pi integral from negative r to positive r of x square root of r squared minus x squared and dx. How do you like it now, right? But wait a minute. Why does this thing look so familiar? Where have we seen that thing before? That's exactly this thing, isn't it? And this was my motivation not to use symmetry, because I did this one during second period, and I want to convince you it's the exact same integral as this one. You know what I'm saying? So this integral better give us the same answer now, which is 2 pi square r lowercase r squared, right? That is my problem. You see, then what does that tell you about the value of this integral? This whole thing. It better be 0, eh? The same donut cannot have two different volumes depending on our method. Do you feel it? Do you see this? It has to be 0. Okay, that one I'm gonna do it separately down here so you can feel it with me. This integral right here. Negative r to r of x square root r squared minus x squared, okay? First, let's try to feel it together. Do you see, is this an even function or odd function, that square root thing alone? Oh, come on, if you replace x with a negative x, do you get the same thing or do you get the opposite thing?
Even.
This is even function, isn't it? X is an odd function, so odd function times even function is odd function. If you evaluate odd function exactly same distance to both sides from the origin, do they cancel? Okay, in case you don't see it, here comes the graph. Okay, do you see this thingy looking like that? What? Okay, let's look at the zeros. When x is equal to negative r, this thing becomes 0. This is always positive, this is negative. When x is equal to 0, it's 0, so it has to go through that point. I mean, you don't know exact shape of this, but it has to connect. And then when x is equal to r, it's 0 again. And that thing is positive, so it has to be positive. You get it? And these are exactly symmetrical. So this all negative area and this positive area must cancel. How about that for reasoning? See, we had quick problems like that in chapter, was it 5? Even and odd function. If it's even function, we just double it and from 0 to r. If it's odd, then just whole thing cancels, it gives us 0. You know what I'm saying? Okay, I'm gonna shove that on the side and I will actually evaluate this so that you are fully convinced. What is the technique of evaluating this kind of integral now? You stop. I'm getting concerned with this class. Du, you get it? So du is negative 2x dx. So substituting back, so what we have is, see, this thing is u to the 1/2 power, and du is x dx, so I need negative 1/2 in front, right? That's ugly. Negative 1/2. Good. And du. Now, more importantly, we change the variable from x to u, so we have to change this limits of integration accordingly. So let's substitute negative r here. If x is negative r, then u becomes 0, right? What about positive r? Well, that still becomes 0 now, doesn't it? So this thing is 0, like I told you so. We have y is equal to sine of x and y is equal to negative sine of x, okay? Let me try to sketch those two. So, this versus, that's ugly. Let me try that again. Something like that. So this is pi right there. So this is y is equal to sine of x, and this one is y is equal to negative sine of x, right? Y'all know what this looks like. I'll call this y1 and this thing y2. Now, I'm going to draw a rectangle. If I draw one rectangle like that, this is a cross section, and then I want to make this thing a semicircle. So what does it look like, right? Okay, I'm gonna do my best to sketch this thingy. Okay, that worked. Does it make sense to you? That's the thingy that we are looking at. This is my dv. So this length from here to here, which I will call y2 minus y1, is this much. And this thickness is dx. You get it?
Oh, so it's only rotating like halfway.
It's not rotating, it's called a cross section. We could call this, we can make this thing square, triangle, but this is, they want this to be a semicircle.
Okay. Oh, okay. So
now,
the rectangle means the base. Okay, thank you. Yeah. Okay.
So y2 minus y1 is this minus this, which is 2 sine of x, right? Okay, that becomes convenient once you figure that out. So let's try to do this. So dv, in this case, is equal to pi r squared, but half of pi, because this is only a semicircle. So I'm going to put pi over 2. And then let's just write r squared dx for the time being, right? And then r in this case is half of this thing, isn't it? This is a diameter, correct? So what we have here is sine square root of x dx now, right? Okay, do you remember how to integrate sine square? Is sine square equal to, and then it's easier to just figure it out from here. Is that thing equal to 1 minus cosine 2x over 2 dx. Say yes. Now we can integrate, so v is equal to from 0 to pi of, I'm gonna put pi over 4, combining denominators, I'm gonna put this thing like this. Good. Now that thing is pi over 4, and then I will have this thing becomes x, minus this thing becomes sine of x, 2x, therefore chain rule 1/2, and then 0 to pi. Now, thing about sine is, once you plug in pi, it becomes 0. Once you plug in 0, it still becomes 0. So the only thing we pick up from here is this pi. So we have pi to pi squared over 4 as our answer. Good. Okay.
Is R,
yes.
sorry, is R y2 minus y1?
Yes.
Or-
Well, no, it's half of this. This is a diameter.
It's half of,
Yeah. So
okay.
we put half of it. Good.
It's, okay, so y2 minus y1 gives you the diameter, and divide by 2 gives you the radius.
Maybe I should write it here. y2 minus y1 over 2. You know what I'm saying?
Thank you.
Okay. So let's do number 25. Okay, e to the x over 2, and I don't know why I did the shell method. I was kind of like too much in love with the shell. But washer method turns out to be so much better way. So let's do this thing with washer. Okay. And then say y is equal to 1. I'm gonna throw that first. Say it's about here. This is y is equal to 1. And then y is equal to e to the square root x. Maybe it looks like that. I mean, e to the x over 2. Good. And then x is equal to ln 3. Say it looks like this. Good. So this is ln 3. Well, I'm going to write x is equal to. No, I don't want to write it because I want to throw the thingy washer. Okay. Now we want to rotate this about the x-axis, right? So let's use washer technique. And you will see this is infinitely better than shell technique. So we have this, and then rotate this thingy about. So this thing gives you the inner circle, and then outer circle. About that? Okay, that's perfect. So this is our washer. How about that? Good. Okay, now this is dV. And dV is equal to pi and big radius minus small radius, right? Big radius square minus small radius. Big radius is this, right? I'm gonna still call it y1 and y2. So this is y1 and this is y2. So we have y2 square minus y1 square and dx being the thickness of the washer. Good. And that will be pi. And y2 squared, that thing is square, of course, it's e to the x. How nice is that, right? And then 1 squared. Wow, this is going to be nice integral, right? And from ln 0 to ln 3 of pi and e to the x minus 1 dx. With me? And pi constant outside, e to the x, still e to the x minus x. And then from 0 to ln 3. Good. And pi here, once you plug in ln 3, e to the ln 3, they cancel. So we get 3 minus here ln 3. And then once you plug in 0, I screwed up during the period. This thing becomes 1, not 0. And the other one is 0. So our final answer becomes pi and then 2 minus ln 3. How about that? Good?
Yeah, Mr. Kim. Can I ask a question about how then when you said y2 equals to y1, how do you get root 3 if you use a shell method? Because I don't get how you can like I just don't know how you find if you use a shell method, how you get the integral parts.
You
like
mean how to integrate?
No, not how to integrate. Like find the from A to B. I don't know what
I don't have that thing open in this. Okay, let me try to sketch what is in the Dropbox note. This was not a good way, but just for explanation purpose, and I don't recommend this. So right like that, right? So we draw it like this, correct?
Mm-hmm.
So we have to find the inverse function, which becomes this. And this is x is equal to ln 3, right? Call that 1, call this 2. So that dv is equal to, this thing rotates this way, right? So 2 pi y being from here to here, times this height, which is x2 minus x1, and then dy, which becomes 2 pi y, and x2 is ln 3 constant minus this thingy. Does that satisfy your curiosity?
That wasn't what I was asking, because
okay.
Sorry, for your integral parts, you put from 1 to root 3. I get the 1 part, but I don't know how you get from x1 and x2 to intersection. How is it at root 3?
Oh, I see. We have to equate these two.
Yeah, and I.
Right, so 2 ln y is equal to ln 3, right?
Yes.
Ln y is equal to 1/2 ln 3, right?
Yeah.
1/2 power goes up, so ln y is equal to ln 3 1/2 power. So y is
okay.
3 1/2 power. How about that?
Okay, thank you.
Okay. Turns out on a Dropbox note, I did this thing twice, 2 different ways, huh? Okay. But that is not as nice. This is so much nicer. You know what I'm saying? So I highly recommend this, doing it in a washer technique. Okay. Okay, let's go to 26. Okay, on 26, we have a hole of radius 3 through a center of a sphere 2. Oh, okay. So I'm gonna throw a circle and then throw the coordinate axis in it. This is there was a similar problem to this, but let's just do it over. Okay. I'm gonna change the color of this thing as well. Okay, So radius of 2. So this is 2. Okay, push this thing down just a little bit. And equation of this is x squared plus y squared is equal to 4 now, right? And radius of root 3, about that much, right? So let's cut this thing. So what we are looking at is this thingy. And then rotate that area around. You know what I'm saying? Okay, so this is root 3. Do you all see it? Say yes. Okay, now, wow, this is really difficult to draw. I'm gonna try to do the best. So whenever we are looking at the circle thingy, washer turns out to be a better way, right? Instead of a shell, because square root is a very nice function to square. So I'm gonna draw this rectangle sideways like this. So we have that thingy. And I'm gonna draw the inside radius. So we have that thingy. Okay, so we have this is our washer. This is, I mean, this is very close, but it's a washer, not a shell. Okay, this is my DB. Okay. Do you happen to know how high this thing is? Do you all say this is 1? Right? 1, 2, root 3, 8? Yeah, that's kind of a key here. So my dV here is pi. And then I need x2 squared minus, oh, by the way, there's no restriction on which one you call 2 and which one you call 1. I just, my habit of calling the bigger one. So this is x2, right? And this is x1. x1 is equal to just root 3, eh? What is x2 equal to? X2 is equal to 4 minus y squared, eh? From this equation right here. Say yes. Okay, and the thickness is dy. So what we have here is pi, and x2 squared is 4 minus y squared minus x1 squared is 3 dy. How about that? I'm gonna make this thing slightly bigger so that it appears to be right proportion. Okay, good. Now we are going to integrate now. So the v here is from 0 to 1 and we double it, right? Integrate from here to there 1 and then we double it. And we put this piece of meat in it, which is 1 minus y squared now, right? You with me? Okay, then we integrate, so we'll have 2 pi, and this thing becomes y minus y cubed, therefore 1/3, and from 0 to 1. So this thing is 1 minus 1/3, which is 2/3. So we get 4/3, but we didn't get the right answer. Where did I mess up? 28 pi over 3. is the answer. Oh, I see. Volume of the piece that is cut out. This is the volume. Sneaky problem, right? This is 4 pi over 3. But amount that is cut out is the entire sphere minus this. You know what I'm saying? Okay. So that was a very sneaky problem now, wasn't it? So the piece that was cut out, volume of cutout is 4 pi over 3 times radius q minus our volume. And that becomes 28 pi over 3 cubic feet. How about that? Good? Question? Okay, then we'll do 36. Okay, 36, we have hemispherical bowl with a radius 8 inches. Okay. Filled with a punch. Okay, so how do I have a semicircle thingy? No, I don't. I'll just go with a circle, okay? Okay, this is the bowl. And then coordinate axis in it. That's not exactly centers better, right? And then we'll just use the lower half, okay? So this is 8 right there. So equation of this thingy is x squared plus y squared is equal to 64, right? So far so good. Okay. How much work does it take to empty the bowl, right? Okay, that's beauty. So, and how much is it? Oh, 2 inches off the top. So it's going to go off up to the 6. You know what I'm saying? So let me write that thing down. So this thing is filled up to here. Good. I'm gonna draw a rectangle. So let's say we take that piece. That's not what I wanted to draw. Hold on. Why Control Z doesn't work? Delete. Delete. That's so weird. Maybe this keyboard has run out of battery. Okay, suppose we have, I'm gonna bring it down a little bit. That thingy right there. Okay, now I usually do that rectangle with the. So if I draw this, what? Huh, that messed up. I think my keyboard is still working. Let me try that one more time. Something is going, something is not right with this. I'm not having a precise control over this computer. Okay, I got it. Okay, this is my disk. Good. And let's get the dimensions. So this is x right here, and this is dy. Good. So that's my dv. Okay, let's just figure out the dv first. dv is pi r squared, which is x squared, and then dy, right? Okay, so I'm gonna substitute So y from, x squared from here is 64 minus y squared dy. Good. Okay, now I'm gonna figure out dF, the amount of force it requires to lift this thing, right? And that is the mass density, well, in this weight density, right? 0.4, which I'm gonna write G rho times our dV. You guys get this idea? Which is just a 0.4 times this whole thing. You know what I'm saying? Maybe I should write 0.4. Right, this thingy is our G and rho together. That's a weight. And then we'll have 64 minus, yes.
Shouldn't be 0.04.
Oh my God. Yes, it is 0.04. Okay. That zero doesn't look satisfying. I don't know why I'm so anal. So far, so good. Now, dW, which I'm going to write here, dW then, amount of work we need to do to lift this thingy up to here. So we need to figure out the distance we need to travel, right? I'm going to have to erase that 6 and write it on the other side. And that's this distance, isn't it? Right? If I just write y, somebody point out what's wrong with y. That sure looks like y. Why is it not y?
It's a negative.
Y itself is a negative number, isn't it? It's below the x-axis, so I have to put negative y in order to make it a positive number. Do you see that? Or, if you will, y is equal to 0 minus y is equal to y. You get it? 0 minus y. Maybe I should just write that. 0 minus y. How about that? So that is negative y, right? Times our dF. You with me? I'm gonna distribute, I'm gonna just write it. So negative 0.04 and y times 64 minus y squared dy. So now I can finally integrate from 0 to, not 0 to, whoa, I almost fell in for that, all the way down here, which is negative 8 here, right? Negative 8 to negative 2, because it's filled way up till 2. Did I write that is equal to 6? You see, this is not correct, right? I'm going to have to zoom in pretty close to change this. Surgically remove that. Okay. This is noise negative 2, right? Okay. So negative 2. Good. Y'all with me? And then we put that thing in. I'm gonna put this constant outside because that parenthesis is annoying. So we have negative 0.04 like that. And then I'm gonna distribute y. So we have 64y minus y cubed. You with me? Okay, now that is negative 0.04 and this is y squared, so we have 32 minus this is y to the fourth power, therefore we have 1/4 and then negative 8 to negative 2. Now most difficult step, right? Somebody punch the calculator and tell me what this whole thing is. I lost pi somewhere.
0.07.
No. I mean exact with the pi. In terms of pi, we have come so far, and then you notice that I dropped the pi. Okay, so I'm gonna, while you guys punch the calculator, I'm gonna fix this and put pi in. Oh no, what have I done there? Okay, I'm gonna bring this thing out a little bit and insert pi there. And I need pi here. This thing just really messed up now. That rewrite that ugly. Pi. And finally, take this thingy out. Put pi. Okay, who's got the answer?
Is it 36 pi?
Is it 36 pi?
Or
Okay.
113.097, blah, blah, blah.
Okay. Looks about right, right? You guys concur? Okay, well done. We have time for this problem. Okay, let's do volume of football, which is kind of what I did already, but let's do it again. We have time. We do have time, right? Yeah, we do. Okay, so let's draw the rectangle. Like so. And I'm going to rotate this thingy. Like so. Okay, so what I have is, oh, that's ugly. Let me give up another crack at it. Slightly better. Good, that's my dV. So my dV here is pi, is that y? The height is here is y. Pi y squared times dx. Now this is easy, right? Pi y squared. Here the equation is x squared. Oh no, not that easy. Where's the, yeah, here's the equation. This thingy, 4 over 121. Why am I messing up? I'll start over. 4 over 121 x squared plus y squared over 12 is equal to 1. So y squared over 12 is equal to 1 minus 4 over 121 y squared, x squared. So my y squared, I need y squared, is 12 times 1 minus 4 over 121 x squared. You know what I'm saying? Okay, so plug that in onto the other side. So I'm going to take 12 to the front. So we have 12 pi, and then 1 minus 4 over 121 x squared dx. Good? Say yes. Okay. Now I can integrate. So v is from 0 to 11 over 2 here, and then double it to use symmetry. And then we have 12 pi, and then 1 minus 4 over 121 x squared dx. Good? Then, so we have 24 pi, and then we'll have x minus, this is going to be x cubed. So 4 over x cubed here. So multiply 363u from 0 to 11 over, this is humanly impossible task now, isn't it? So we do it in our head. 88 pi. How about that? By drawing this circle. Say there's this circle. And I'm gonna put the coordinate axis in the middle of it. Like so. Okay. And then we are going to drill a hole, right? And then radius of that hole is square root 3. Okay. So the equation of this is x squared plus y squared is equal to 4. Do you see that much? Right? Sphere of the radius 2, so this is 2. And square root 3 is 1.7-ish. So I'm gonna draw this thingy. Oh, not like that. I'm gonna exaggerate and make it a little bit big. Something like that. So what that tells you is this is square root 3. I'm gonna make it just the upper half like that. So that's the only area we need, and this is square root 3. So first of it. Okay, so we will rotate this area around and then create, and we'll use the symmetry to double it to find this little ring looking thingy. How about that? Okay, in order to figure out the dimensions, I need this thingy. This is very similar to the example that I did. Wait, that was, well, whatever. Okay, so we know that this is 2. Good. Okay, that's where we're going to start. Now, we need a rectangle, and we figured out from the experience with a donut, whenever you have a circle, washer is a better, superior method, right? So I'm going to draw the rectangle right there like that. Okay, so now, and rotate that thingy around, so we create this looking thingy. And then I need outer. You all get the picture? So we need that thing. Good. So that is going to be my dV. And then it will have pi of some outer radius squared minus inner radius squared, isn't it? I'm going to write it as r for now. And then thickness, this is dy. With me? And this is the difference of square. Let's remember that. It's not quantity square. Okay, now we need the outer radius. So outer radius is this much, isn't it? And that much is x, isn't it? Our x, function x. Good. And then this much, we need to know how much this is. And that's a square root 3, isn't it? This thing is square root 3 from here to here. Do you see that? And then do you know how high this side is? This thingy? This side is 1, huh? Do you see why that's 1? This is 1, 2, square root 3, 30, 60, 90 triangle. You get it? Okay. So now, so this is equal to pi, and then we have x squared minus, and the small radius is 3, dy. So far so good. Now we have to substitute. See, we always have x and y, some form of x and y here, but we have to replace everything and convert it into this variable, which is y, what we are integrating with respect to. So we get it from here. That was weird. So we have pi, and this x squared happens to be 4 minus y squared. Very good. So finally we have 1 minus y squared, and dy is our integrand. Now we are ready to integrate. So we'll say from 0 to, now we have to be careful, it's not x that we are looking at, from 0 to y is equal to 1. You get it? That's where this thingy exists. So 0 to 1, and then we'll double it using symmetry. We good? Okay, so we'll have pi and then 1 minus y squared and then dy. Are we good? So that is equal to 2 pi, and this becomes y minus, this is y cubed, therefore 1/3, and then from 0 to 1. Okay, substitute, so this becomes y, this becomes 1, this becomes 1/3, so we have 2/3 times 2 pi, so we have 4 pi over 3. Good. Okay, tangent theta. And the reason for that is, I want to know what this thingy is, right? 1 plus 4x. This is not letting me finish this work. Now we're in a maximized window mode. Let's see if this thing works. 4x squared, right? And once you plug it in, plug this thing in, then it becomes 4 plus, that becomes 1/4, which cancels this, so we have tangent squared theta, right? And that happens to be secant square, and take a square root. So far so good. Now we take dx, which is the derivative of this thingy, so we have 1/2 of secant square theta d theta. Good. Okay, so now let's see what we got. So we have that 2 here, and we have this thingy times this thingy. So we have secant cubed, and 2's cancel. So we have secant cubed theta d theta, and it runs from when x is equal to 0. So 0 here is theta is equal to 0, and when we put 3 here, 3 into this, so that's inverse tangent of 6. Good. Now I'm regretting agreeing to hand evaluate this with all this trouble. Okay, now this was, if you remember, very ugly integral that we did before. Can I refer you to that video in order to save time? Or we can go ahead and do it. But it becomes very ugly integral that gives you, if my memory serves me correctly, I think it gives you question mark 1/2 of secant theta tangent theta plus ln secant theta plus tangent theta, and inverse tangent of 6. I think that's what you should get, but you might want to check that one out. Okay, so for something like this, typically the AP puts it on a calculator section for this kind of reason, because they don't really expect you to be able to do this much. Good. Okay, now let's go on. So we have a ball with a radius 8 inches. Let's just start there. Okay, I'm gonna throw a circle. And the coordinate axis. Whoops. That looks about like the center. Okay, so the equation of this thingy is, I'm gonna write it up there because we just need the lower half. X squared plus y squared is equal to 8 squared. Eh? So far so good. Okay, then now there's a punch filled up to 2 inches to the top, so right there, right? So let's draw this one rectangle. If it lets me draw the rectangle, oh boy, huh? Somewhere here. And then rotate that around and create a disk. Create a disk. It'll eventually get there. Like that. And then that's the disk we create. Good. So that's my dV. Okay. Now I'm gonna start writing dV. Okay. dV first. This dV is equal to, this much is x and this much is dy, isn't it? So we have pi x squared times dy. Good at the moment? Now we need to find the, well, actually, and then pi, that x of course in terms of y, so we'll have 64 minus y squared dy. Good? You with me? Now, then we need dF. dF is amount of force that's required to lift this one slice of punch. Okay? And that, of course, is the density, weight density, which is given right here. You know what I'm saying? So 0.04 times, there it goes again. Oh, it didn't crash, right? Times our dV. Do you get that part? Right. Then times the volume is the weight, which is the force. Good. Okay, now substitute the 0.04 pi, and then we have 64 minus y squared and dy. Good. So that's dF. Finally, we need the work that is required to lift this disk all the way up there. Good. Now, you might think this is just y then, isn't it? You might think this is y right there, but it's not y. Now, why is it not y? This is 0 minus y. You get it? Do you see that? This line is where y is equal to 0, and this is where y is equal to y. Y itself is a negative number. Maybe I should write 0 minus y, so that's very clear for everybody. You with me? Because y itself is a negative number, so dw is equal to negative y times df. Good? Say yes. Okay, so that is, I'm gonna put it in here, so it becomes negative 0.1 over pi y minus and the times 64 minus y squared and then dy. You with me so far? Okay, now we can integrate. So volume now, where does this thing exist? It exists from all the way down here, which is -8, and up to the place where -2 is, right? Where the punch is filled up. So we have -8 to -2 of this thingy. Just do it like this, -0.04 pi, and I'm going to distribute, so 64y minus y cubed and dy. How about that? Good. And after that, it's pretty downhill, and then you should get that kind of answer. Good. Okay. Now let's do number 52. 52, what is the, we are trying to find the surface area of this thing, right? Okay, so let's draw this thing about there. Okay, and we have this function that looks like this. Y is equal to 1 over x, eh? Okay, starting from 1 to 2, well, y is equal to 1 to 2. So it only exists when y is equal to 1, we should cut it off right there, right? That much is the only part. Good. So I'm gonna take this and throw that thingy and call that ds. And now I'm going to rotate this. If it lets me. Okay. Okay, that's not too bad. So it creates that thing. That's my dA. Good. So let's run this thing through. So we first need ds. In order to do ds, we need the derivative, right? And looks like we are differentiating with respect to y because y is given as a range. We can convert it, but why bother? So let's have this x is equal to, actually I'm gonna write it here. I'm gonna erase this thing. And then let's say x is equal to 1 over y, right? So dx dy is where we start. I'm going to zoom in a little bit. Okay, it doesn't want me to zoom in, so we'll just work with it. So this is y, so -1 power, so we have -1 over y squared. You with me? Okay, now I want to square it and put it inside this thing called ds. And ds is 1 plus that thing squared, isn't it? So we have 1 plus 1 over y to the 4th, and then dy. So far with me? Say yes. Okay. And then somebody check the answer key. This is, I believe this is a calculator problem, right? Okay. Now ds then, dA is 2 pi times the rotational radius, and rotational radius is this much, isn't it? Which is x. So 2 pi x times ds. Good. So that is 2 pi x Our x is this, right? 1 over y times square root of 1 plus 1 over y to the fourth, and then dy. You with me? And finally, our a is from 1 to 2 of all of that. And then you plug that into the calculator. How about that? Good? Questions? I think that is our last one. Okay, then we're going to move over to chapter 8 questions. Okay. And we have 39 and 61. Okay. So let's look at 39 first. Okay, 39 is really, this is infinity minus infinity, right? So which one wins? What kind of infinity is it? Do you get a feeling that this one wins and this whole thing will turn out to be infinity? And that relates to today's topic because this thingy grows faster than this thingy, right? Linear function shoots up like this and this thing curves this way, so it'll get there first. Like, not all infinities are created equally. And first thought is this. We'll take a common denominator, and common denominator, of course, is this. You might think, don't write this because I'm going to erase it. That's one way, but right? And I believe this will work, but I have a better idea, and better idea is this. This is your common denominator. Really? How is that a common denominator? Watch. See, it's a common denominator, isn't it? Wasn't that clever? Yeah. So what we have is, this is 1 minus x to the 1/2 power. How about that? Good. Now let's check. So as x approaches 0, denominator approaches 0. Numerator does not approach 0, it approaches 1. You know what I'm saying? So this will have a form of 1 over that thingy. And this is infinity. So we cannot L'Hopitalise this, because L'Hopital's rule only works on 0 over 0 or infinity over infinity, and this is not one of those cases. So this is it. You get it? Okay, well done. Okay, let's look at this thingy. A, oh, this A has been cut out. I think I want to enlarge this a little bit. So this is A. Okay, domain of this thingy. Let's try to see, exponential function is okay, no problem, right? So what we care is this thingy now, isn't it? So where is our restriction here? Hold on a sec. Okay, I'm gonna graph this thingy inside that function. I'm gonna put them here. Okay, now this thingy is just 1 over x, this like that, but it raises by 1 unit, so I'm gonna throw the asymptote about here. This is my asymptote. Okay, and then my function looks like this. Doesn't it? You with me? So far, so good. Now we have to think about the base of the domain of this entire exponential function. Okay, so At the moment, we just take out the 0 as our domain. So first a little bit. What is the only part, what is the only rule when it comes to exponential part? This is not technically exponential function, but what is the only thing that we are required to consider? Our base need to be positive, correct? There's no such thing as a negative base, and if you want to take a power that gets crazy, I mean, you're looking at complex numbers. So base is positive, right? So let's think about it and try to sketch this thing. So we are taking this case over here, right? So this part is good. And then all of this part is good. You know what I'm saying? And do you see why you have this kind of domain? Do you see this is -1 right here? So this becomes your domain right here. Now, and then B part. This f of x reaches -1, okay? Okay, let's do that part. So part B here. I'm going to do it with that. Oh boy, this is the last one, part B. Okay, so limit of 1 plus 1 over x to the x power as x approaches -1. Good? Okay, now, let's just check. If this thing reaches -1, this thing approaches 0, doesn't it? 0 to the -1 power. 0 to -1 power, what is that? That's kind of like this idea, isn't it? So this is not technically L'Hopital. This is not what they call indeterminate thingy. We expect this thing to be infinity. Okay? Well, from the left-hand side, because this thing doesn't even exist on the right-hand side. Okay, but we'll just proceed anyway. And limit and x approaching -1 from the left-hand side. And this is a giant technique. And then we put ln 1 plus 1 over x to the x power here. We can put it right here. So far with me? Now we can see this thing a little bit better. If this thing approaches -infinity, let's just take a look. I mean -1, so this thing becomes -1, right? And then, if this thing approaches -1, this approaches ln 0. What is ln 0? That, right? So this is e to the infinity, which gives you infinity, which is kind of what we suspected. How about that? Good? Questions? Nothing? Okay. Then I'm going to stop. Yes?
Why is ln 0 negative infinity?
Oh. Let me draw the graph of ln. It looks like this, right? So that side is -infinity. Okay. Any other questions?